Hello to viewers, welcome to my channel Science to Technology. In today's show, Science Thursday, we're gonna talk about Vimag Labs virtual magnet synchronous motor, blah blah blah. So let's dive deep into it. So why I'm talking about this? Well, if you have watched my channel, I've already covered this 4 years ago, but hype is the primary reason. It's like Vimag Lab makes a motor that challenges China's dominance on a rare earth magnet. I'm like, we never needed rare earth magnet, but okay. It's like, India's virtual magnet synchronous motor. That's the silliest name there is, but okay. More efficient than permanent magnet? Yes, I'll explain that part. That's good. That's good. India's magnet-free motor stumps China. It's like, they know how to manufacture it. They are mass producer of it. And Caleb is the only one so far. Again, I could be wrong. I hope I'm wrong. But I could not find enough detail. Like this is the only low resolution photo. This photo is going around, which is AI photo. And this is the only person who apparently has a behind the scene access. He does upload a small, very hyper low resolution video. He might be releasing that video soon. When I'm making this video, it's not there. But he is the only one that showed the rotor and stator. It did not show the cool part of the rotor, but okay. So hype has been going bonkers on this, which is really sad because there is amazing thing in this and they're talking about the dumbest thing about this. So let's dive deep into it. So what's the core? Well, core is what we call ancient technology, as in, I have a book that was published before moon landing. It has it. It's called a brushless AC synchronous motor, so to say. Now be mindful, we used to make generators with this philosophy, like hydro dam generators before 1950s. Like you could have just gone and bought from General Electric. They're like, yeah, we have this, take it and go. Like, wait a minute, why I'm talking about generator? Motor and generator are the same thing, literally. Every motor is a generator, every generator is a motor. It's all about basically how energy is flowing. For example, if you have this motor, you will have regenerative braking, right? Same thing. So all motors are generator, all generators are motor. So we started the philosophy basically having an exciter, spinning diode and a rotor that is creating the actual magnetic field, and the stator that was done in 1950. Now be mindful, we could have done this before that, but there was no technology to make spinning diodes robust enough. There were some designs where they had like a permanent magnet generator on the same shaft that was creating power. That power was being leached off using mercury arc rectifier. They were feeding it into another coils. So, and you're like, okay, why would you want to go through all this hassle? Why not just have a permanent magnet here? You will not get control. If you are trying to make a generator, you have to have the ability to control basically the voltage without affecting the frequency. Meaning power plant generators, they are locked RPM, meaning they are synchronous. So if they're supposed to rotate at 1500 RPM, in case of India 50 Hertz, they're supposed to rotate at 50. You can't, oh, voltage is going up too much because let's say somebody reduced load from it. That's not allowed. Your RPM must remain 50. So how do you control it? Well, you reduce the rotor current. That's why people want to have that. Because again, stator control, you can do that in every single motor. Rotor control, you can only do that in this. That's why this was loved, darling of every single hydro dam. So you can control the rotor current. So it's like, hey, people are putting load into it, voltage starts to stack down. You don't need to increase the RPM. You just increase the current that is going into the system. And voila, you get high voltage. And again, it goes the other way also. So most generator that has big enough size generally would be this. So you'll have a rotor and exciter. Both are basically the same thing, using induction to jump power without having the brush. Oh, coal power plants generally use brush. Why? A diode does have a little bit of lag. And in hydro dam, you do talk about turbine blades, which are like, they're not tight. Let's just put it that way. When you're talking about coal power plant, those puppies are tight. So their brushes are stable. Here, brush won't be stable. So we just use brushless technology. So this is what we call brushless AC synchronous motor. Now here's the problem. Only induction motor is true self-starting, meaning if you have AC sine wave coming in, you plonk your induction motor, three-phase induction motor on three-phase sine wave, it starts. The end. Nothing. No problem. You want to change the rotation direction, flip two of the phases. The greatest motor. There are brushed motors that can self-start, like a universal motor, but if I'm not talking about brush, like a reluctance motor will not self-start, BLDC will not self-start, permanent magnet synchronous motor will not self-start, a reluctance motor will not self-start. Only induction self-starts if you have a AC main space. Why? Because it can tolerate slip and can generate bonkers amount of starting torque. However, somebody was like, hey, we want this motor. Why? This puppy can run at power factor of 1. Let that sink in. Power factor 1. Meaning, if you look into transformer that is nearby you, the pole transformer, house transformer, whatever have you, they generally say kVA, kilovolt amps. Like why volt amp? Simply because that much power, like let's say it's 500 kilovolt amp, you can get 500 kilowatt out of it, but power factor has to be 1. If power factor is 7, you lose 30% of the capacity because of the power factor. And again, it's a real energy loss. On mathematics, on paper, the magnetic energy just bounces back between your transformer and your inductor, as in like these coils are acting as an inductor, but reality is we don't use superconductors, so that energy does get dissipated. That's why large factories, they get charged for poor power factor, because again, somebody has to pay for the transformer. So these puppies, when you are talking about big industrial loads where like I turn this motor and turns off during maintenance, they're like, bro, even 1% extra gain is like shut up, take money. Synchronous motor. But again, this does not start, it does not self-start unless you have like super duper tiny magnetic rotor with a lot of gear, like your microwave plate. You have seen that? That is synchronous motor. So how that starts? Super gear down and very tiny rotor. So it can almost snap like, but any real load, it will not start. So trick is hybridize this puppy. You take this puppy, you insert a squirrel cage into the rotor. You force it. It's like, you force it. Once you force it, that will provide the starting torque. You do not feed AC, power into the rotor. You just let squirrel cage start the system, get into the right RPM. Once it's like, let's say they're supposed to rotate at 700. Once you reach 650, then you start to inject current. So it will cancel out the slip. Induction always needs slip in order to work. This will cancel out the slip, slowly go to lock. At that point in time, it's just dead weight. And then you can control based on the load. Let's say you're running a cement clinker, how much load is there? You can easily adjust the rotor current, and voila, power factor will be at 1. And yes, this sort of things can have been done from 1950s. We have been doing it. So very amazing motor, no brushes, no magnets, large size available, power plant scale available. It's just that we had to wait for electronics to become cheap enough, because nowadays you will not even get, India has world's most efficient motor made by ABB, 99.13% efficient. Exact topology, same topology. But again, modern synchronous motors do not have squirrel cage. So how do they start? They rely on VFD. The idea is VFD is going to give you that 1 hertz. So it will slowly impart torque, 2 hertz, 3 hertz. Then it will slowly let it reach the 50 hertz mark. So you do needed technology. Like again, motors sorted in as early as like earliest documentation is like 1870. Practical use 1950. We had to wait for 1990s for VFD technology to become good enough. Like this book is old enough where it's like, it's not even talking about silicon rectifier, it's talking about selenium rectifiers. It's like, yeah, that was the cool high tech at that point in time. The spinning diodes were the weak link at that point in time. So they were like, there are some new research going on silicon. I'm like, yeah, it will become important in future. So by 1990s, we had the silicon technology to create AC waveforms of whatever frequency we want. VFD, variable frequency drive. So these puppy became mature and cheap enough. So now everybody's like, hey, we can shrink this puppy. These things are generally designed for low frequency, like mains frequency, 50 hertz. Why not shrink it to 400 hertz? That is your electric vehicle territory. So core is sorted. Magnetless motor is like we had it from day one. That's nothing new. It's like take it and go. Multiple companies make it, multiple brands makes it. This is like sorted, done, ancient. Now you have to understand why people are going through so much hassle. Well, here's the deal. Topology does come with some penalty. For first example, it's going to be huge. It's going to be big. Like if I give you an induction motor and if I give you synchronous, even if it's a brush synchronous, you have that space for brushes. So now it's bigger. So it will always be bulky. Penalty, it will always have poor power to weight ratio. That's one penalty. Second, complexity of manufacturing. When you're talking about squirrel cage, yeah, it's a bit messy, but it's super not involved, so to say. It's just stamped steel, welding, blah, 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 go home. Reluctance, super easy. Sheet metal, done, go home. But when you're talking about like needing electromagnet there, that's an expensive thing. So that is a fundamental problem. It is complex in manufacturing. But again, manufacturing complexity is a one-time deal. Once you figured out how to automate it, it's a solved problem. It does require complex electronic drive because again, you do have basically secondary power source, secondary set of stators that you have to control in order to send power to the rotor. However, why go through all that hassle? The best, widest operational range, meaning you get BLDC motors. right now darling of the world, a permanent magnet synchronous motor. What's the good thing about it? Super high torque at low RPM, meaning you press your accelerator, car goes from 0 to 60 like there is no tomorrow. This puppy has torque with some extra torque, with some more torque and high efficiency. So again, induction motor does have a bonkers amount of torque, but it is horrendously inefficient. And that's why if you look into any AC compressor, they say lock rotor current. Yeah, it will fry everything. It will try to rotate it, or it will fry everything. BLDCs or permanent magnet synchronous motor, they are like, yeah, we got this. We can give you the torque and we will not burn up. So that's the lovely part. People love it. But that very thing, that magnetic core, that strength that is there, that backfires at high RPM. The moment you want to increase the RPM, it's like it starts to fight, because again, back EMF is very strong. You can't make the permanent magnet weaker. So they're like, field weakening and all that. It's like, Basically, the thing that makes it great at low RPM is the very thing that makes it weak at high RPM. So that's why the range is more geared towards lower high RPM systems. High torque scenarios. Induction motor, super cheap, that's the good part. Self-starting, really cheap part. Great at high RPM. That's why Tesla's first systems, they were relying on induction motors. But again, it needs to be at high RPM in order to really give its wings, so to say. So they were stupid RPM, as in above 20,000 RPM, as in there was no bearing manufacturers that can like certify a road rated bearing at that RPM. They're like, dude, this is stupid. So they're like, okay, there was one bearing. That's like, okay, if you remove the seals, have it oil flooded, maybe it will last. Nowadays, you can buy almost 30,000 RPM wheel motor bearings. But that time, back then, it was like a big risk for them. But again, at high RPM, it's great. But again, at low, it will burn too much energy. So permanent magnet, great for low RPM. Induction motor, great for, cruise control and highway speeds. Reluctance motor, super cheap, the cheapest. Again, the money goes back to your basically motor driver controller, but holy crap, it has poor power factor. It makes the induction motor looks clean. This puppy is ugly when it comes to power factor. Like, it is brutal. It's bad. And you were like, okay, why not have power factor correction? Power factor corrections protects your downstream things. As in, like, let's say there is a transformer, your VFD will protect the transformer for poor power factor, but VFD has to deal with the power factor. It does not disappear. You inherently want there to be no power factor correction requirement. And like, how the heck induction, basically synchronous motor can do that? Please watch the video that I've linked down below. There is an experiment, a school kit, and it's like showing you increase the rotor current, it becomes like, capacitive or inductive or resistive. You can choose. So induction, great for high RPM. Reluctance motor, super cheap, but when you're talking about this sort of coil motor, basically synchronous motor, now you can control it. You're like, hey, at super duper low RPM, I give bonkers amount of current in the rotor, so I get GG torque. When you are cruising in a high speed, let the way you're just like coasting, you can be like, hey, rotor current goes down to very low. Just go very low. You're like, okay, what if you are going down a ramp and you do not want to slow down? This will start to slow down on its own. Why? Because again, it's a magnet. It's acting like a generator. You can't turn it off. There you can turn it off. It's like off. And when it comes to braking, that also gives you a lot of control, where it's like, hey, I want to smooth the operator brake. Slowly ramp up. Basically, there will be a curve, brake directed, increase the rotor current slowly. Emergency detectors, like apply the brake, slow down the vehicle as much as possible. It will ramp up the current first. Again, it will stress the vehicle, but again, emergency brake means you messed up something. Stay alive is higher priority. So that sort of control is available. You can allow it to coast. You can allow it to stroll downhill without any issue. And again, if you're like, hey, I want to retard the speed, let's say on a truck, increase the rotor current. That control factor, everybody can control the stator. Only this design allows you to control the rotor. So that's why we pay attention to the system. And the electronic circuits that used to be the bottleneck now is super cheap. Everything else became expensive, but electronics did become cheaper. So the control logics and all the messy things that you have to do is like, That's why reluctance motors are being used nowadays. We knew how to make those. It's just that cost of the electronics never made sense. So what did they patent? Because they talk about, like, oh, we patented. There is some amazing patent. Let them be clear. All patents, A, they are very openly transparent to public because they have to be. Second, they only last for 20 years. Meaning this motor, whoever invented it somewhere in the 1840s, the patent would have been there. It would have expired after 20 years. It's now in public domain. You cannot repatent it. Again, unless you have corruption and all that, but generally you don't. And that's why it has to be in public domain, so everybody can tell, hey, dude, you're repatriating. It's a, like, self-fulfilling systems. So what did this company patent? The magnet motor? No. Magnetless motor? No. So Vimag trick is exciter. Basically this puppy, the exciter part and spinning diode, they are using this exciter rotating transformer, as they call it, to do three things. Not one, three things. Generally, first thing, power transfer. Basically have a frequency, a low frequency going into the stator, exciter stator, sending power via induction to the rotor, basically exciter rotor, and that going into DC, as in bridge rectifier. Bridge rectifier makes it DC, DC goes into the rotor, rotor becomes the electromagnet. So that's the first part. You can buy it. There is at least 5 to 6 companies that are making it for electric vehicles. You can just like buy it. That's not a deal. So what did they patent? They patented is using the same pathway, they can read the temperature of the rotor. Like, wait, how? Well, they're reading the temperature of the coils. Because you have a coil, you have such a long path, you can actually detect the resistance. And based on how the current is behaving, you can figure out good enough accuracy what is the resistance of the system going through all this wireless hassle. It will not be very precise, but better than nothing. So that is one thing. Again, it's not neither here nor there from a utilitarian point of view. And then they have black magic technology, which is rotor position tracking. If you know anything about any sort of motors that have ability to switch, they also come with the side effect that they can switch backwards. Meaning, if you're like, okay, I'm gonna turn the accelerator, it's gonna go clockwise, it might spin backwards. It might actually do that. And there had been scenarios where, pro-grade electric cars had this issue. So right now, if you look into all electric cars, they have an actual encoder that tells the rotor position. So switching, basically on phase A, phase C, phase B, the switching pattern never backfires, because again, it has the absolute data from rotor coming from encoder. But encoder is extra hassle, extra stuff. What if you don't want to have it? Like, you must have seen the cheap drones, they do not have encoders. And whenever you turn them on, they will do, they will start to do jerky motion. That motion is there to figure it out, like what's happening. It's very difficult to figure out. If you have spin rotation going on, you can easily tell whether it's clockwise or a counterclockwise. That's super easy. Heck, you can even tell the angle. Super easy, take it and go. But you're like, okay, it's off, it's not spinning. Now tell the system, it's like, oh, okay, we're gonna jolt it. That's the cheapest thing to do. Now there is a what we call high frequency injection. This company figured out to do that, but on an AC motor, which is a synchronous AC motor, and doing it on a same rotor, exciter rotor that they are using for power transmission. Meaning this system literally has two waveforms going through it. One primary power delivery, low frequency waveform, high frequency, that is for position detection. That's the black magic part. So when it's spinning, it's gonna give you phase A, phase B, phase C, and you're like, you can easily tell them apart. Duh, super easy, who cares? However, how do you figure out when it's off? Like when, vehicle is off, you turn it on, how the heck you detect it? This happens, which we call figure 8B. Now, what it's doing is basically stator part is screaming a high frequency signal onto the carrier frequency. Now, again, at 0 point, it may not have the base current. Is just like figure things out, wake up the system. It screams high frequency. Now that high frequency goes there into the rotor and bounces back. Every magnetic system does that. When it bounces back, you will read all the phase. Now, because you injected the high frequency, one phase where the alignment is the perfect, you will have 0 line, no data. Other two will be 120-degree offset signal. Ta-da, you know the exact position, exact angular position. Like, wait a minute, that sounds weird. That's exactly same technology utilized from 1950s in what we call a resolver. This puppy. I have linked the video down below. So what you have is a reference signal, which you are sending, high frequency signal. And there is coil. One coil is 90-degree apart, which we call a sine. Another 90-degree apart, which we call cosine. And because it's a high frequency, it will work even on a zero motion. If you send DC, DC requires spinning. That's why we used to use it for generator first. So now you can make high frequency without any issue. So that reference signal will go based on the position of the rotor, where the rotor is. You can easily figure out a sine will have high value or cosine will have high value. Subtract these two, they will destructively interfere. It will give you a new waveform. That waveform is your rotation. Basically where you are exactly, precisely. Again, this is resolver mathematics. For mathematical reason, they only have two poles 90-degree apart. For this, they needed 3 poles, so it does become a bit more mathematically complex. But again, as I said, electronics is cheap. This was done in 1950. That time, semiconductor was like maybe. This now is like, brah, who cares? Like your Arduino can do that in background. So this is how they are figuring out at 0 RPM, meaning dead start the system. It can figure out where exactly the magnetic poles are, exactly. And because it's deadlocked with the shaft, it knows the exact rotor position, exact one. This is the black magic they have. This is what they have patented, rotor and position tracking. I have no idea why nobody is talking about this, but it is what it is. It is clever. Like, you are reading 3 things. Again, rotor temperature, I do not see the value in it, but hey, better know it than not know it. And rotor position tracking, that means now you can remove one extra component. That is valuable. So these are good things, and doing on the same hardware, that is clever. That is clever. So that's the patented part. Now, what can we expect in the future? Well, here's the deal. I like the technology. I like the company. If you have watched my basically motor videos, I have been talking about this for years. However, I hate the dead hypes, brain dead hype scene that has been going around, and like, you know, stupid reporting. I'm like, they're talking about the dumbest thing. Oh, it's a magnetless. It's like, yeah, we had it from 1950s. You could have just bought it. We had it. It's not new. It's ancient. And the magical part that truly took me time to understand is like, damn, that's clever. Like using sine, cosine. Okay, people in 50s were smart with mathematics and stuff. And these people are doing with 3 angles. I'm like, that's clever. That's good. But nobody's talking about that. So it's a really, like, it cheapens the magical part of it. It's like, oh, it's a 50-year-old externally excited synchronous motor. Again, do not know the name of the motor's technology. There is no agreed upon name. That's why I said brushless AC synchronous motor. And I do not like how this again, if you watch my the basically carbon battery guys, I was like very angry. It's like, why you're saying it's photosynthesis? It's not making glucose. It's completely different. Like, I hate that whenever companies do that willingly, where it's like, if it's something, if basically a reporter messes it up, it's some completely different when the CEO who knows what's going on messes up. I hate that, because it's almost like, oh, you are Indian, illiterates, you can't handle it. It's like, dude, we have engineering colleges. Now, I might be illiterate, but even I could figure it out. So I can guarantee you, this just rubs me the wrong way. And tech has spoke. Let that be very clear. This is the future. We gonna have it one way or the other. Oh, by the way, this is from different brand. I have linked 2 brands, 3 companies. Basically 2 brands that are doing the wireless one. Nissan is directly using brush one. They're like, hey, brushes does not wear out. It's like, what? Your car already has an alternator. It has brushes. It does not wear out that much. Slip rings do not wear out. Split ring does. I'm pretty sure you have studied slip ring and split rings in your childhood. So look into that to figure that part out. So it's a known thing. It agrees. It exists. But neither of them have the ability to tell you the rotor angle on dead start without requiring any encoder. So that's a good thing. But nobody's talking about it. So there is a scope there. However, they have to reduce the price of. This is the only image I could see that a YouTuber I talked about who got the back end view. This is the only video. You can see, like, there are 3 main wires for the primary stator, and then you have 3 white wires that are for exciter stator, and that is feeding the position data and everything else. So they have to make it cheaper, physically cheaper. Like, the item has to be cheaper. Like, okay, magnet is expensive. No, it's not. It never was. We have always known how to do all of these. It's just that magnet was cheaper. It's like, we knew how to do reluctance motor in 70s. We didn't use it because magnet was cheaper. Now magnet is becoming expensive. People are like, okay, let's switch to reluctance. I have no idea why people think magnets are expensive. It's like, no, magnets are cheap. That's why we used it. Now magnets are becoming expensive. It's like, okay, let's throw it away. It's not new. We have always known this. So fundamentally, they have to reduce the cost, because the primary vehicle that this scale can work is a e-rickshaw. It's a low cost trike in India, which is very popular, but super duper low cost. They don't even use permanent magnet synchronous motor. They use its dumber cousin, which is brushless DC motors, because again, it's cheaper. So I'm like, in that market, you can't sell this motor. It will be too expensive. So again, the technology is great. And I'm like, hats off to whoever engineered this. And I'm like, I want to shake hand with the mathematician who's like, okay, I'm going to tell you angle on a freaking 3 cosines. I got this. I'm like, what are you smoking, man? So that's great, but you know, they have to make this cheaper. And again, I do not even want, I don't even want to discuss about the cost of the electronics. It will be expensive. So that's what it is. So let's see what happens in the future. So this was my presentation on basically the hype that is going around. I hope you have liked it, learn from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you have enjoyed it, click the hype button. If you didn't like it, didn't enjoy it, I urge you to press dislike. But before you do that, please open the descriptions. I have explained all the videos. Please do so. And please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free. And as always, thanks for watching.